So chapter 5 for Calculus 1. This whole chapter is pretty much on finding the area beneath the curve. It's the entire idea. And let's say you want to find it from A to B. So we want that region in here. So this is actually a pretty good read in the book. It's just a little short sub blurb on Archimedes. Archimedes came up with this method. It was called the method of exhaustion, but most of us know it as the rectangle method. Now known as the rectangle method. So we can approximate the area by dividing it up into n regions. And making a rectangle using the curve for the top. Let's say for my picture, I'm going to use n equals 4. So I could cut this region in half and then cut each subregion in half. And that would give me 4 regions. Now I have a couple options. I could make the region use the left. I could make the region use the left side of the rectangle as the top. That's using the left endpoint. I could use the center. So this would be the midpoint for the height. These are all, how do I choose the height? And I keep fucking hitting that thing. And the other option that's common is right. So right endpoint. 3 major options. And I'm going to grab this last little piece right here and blow it up and like point out a little bit. Let's look at that last section. So I had something like this. depending on what I choose, if I choose the left endpoint, I'm only getting this part. So I'm underestimating the area. If I do the right endpoint, I'm getting extra. So the right endpoint overestimates. And the midpoint does a little of each. If I do the midpoint, I have extra here that I shouldn't count, but I'm missing some here. And so this tends to balance. But this problem with the left and the right was only if we had a region of increase. If you look at something where we're going downward, you can now see that the left would overestimate here. You get that extra stuff right there. And the right would underestimate. Because it would be missing that part right there. There's a bunch of ways to do it. There's a trapezoid method. There's a lot of methods for doing this area thing. But the rectangle method was this. Just break it up into rectangles. And if we wanted to decide, how wide is each box, here was the height in every case is f of x at some point x naught is the height. Whether it's xl for left endpoint, xm for the midpoint, or xr for the right endpoint, we have f of one of those. That's the height. The width, we need the width for a rectangle too, though. So what's the width? Well, we're taking this distance and we're breaking it up into n parts. Break the distance up divided by n pieces. And the distance is b minus a. So we have the width is b minus a over n. They usually call this delta x. It's the change in x. And so we find the area of this area under this curve. By adding up k equals 1 to n rectangles. Which would be k equals 1 to n f of x k. We don't know which point it's going to be. It's going to be times this delta x. So that's like length times width. I actually don't think we cover that formula till like 5.4 or 5.5. But where we use more of it. Well, you can see there's error in this. Let me pause. Let me let everybody absorb the shit out of this. I can almost get 2 full pages on here. Look at that. Boom. Wide lens. The big takeaway right now, like I got a little ahead of myself on this delta X and using the formula. We will use it later. You don't need it for this chapter or this chapter 5.1. But the idea is like, this is what we're doing with the rectangles. Does it make sense to try to find the area like this? If you don't have any other way of doing it, like we know they have formula for an area of a rectangle, break it up into rectangles. Well, ideally, you could make that the error from each rectangle smaller if we just make smaller rectangles. Make the rectangles narrower and narrower. We want n, as n goes to infinity, the error in approximation goes away, goes to 0. You guys a little bit longer to write it down. This little tasty tidbit right here is called a Riemann sum. And we'll do more with this. We'll do a lot with this in 5.5. For those of you ready to get started on the next step, I have a project for you to do real quickly. We are going to have f of x equals 1 minus x squared on the interval 0 to 1. Find the area using 4 rectangles and her left endpoint. And I have something for Desmos, but since people are still writing, I don't want to switch to that yet. Wait, I'm doing right endpoint there. There we go. Curve is 1 minus x squared. Find A4. Help get a better look at it. This is what it looks like on Desmos. I think I'll post a link to this later on because this is kind of a fun little simulator for Riemann sums. Make sure everyone's on the same page. What would be the width of these rectangles? 1/4, right? This distance is 1 minus 0. We've got 4 rectangles, so 1/4. That's our width. So for rectangle 1, the left endpoint would be 0, so you're doing f0 times 1/4. For rectangle 2, you're doing f of 1/4 times 1/4, and so on and so forth. Right, so we got R3 and R4. This would be F at 1/2 and F at 3/4. We've got 1 minus 0 squared times 1/4 is 1/4. 1 minus 1/4 squared times 1/4 is 15/16 times 1/4 is 15/64. Maybe I'll write these in terms of 16/64, so that would be 16/64. Here we got 1 minus 2/4 squared times 1/4, which is 4/16, which gives me 12/16 times 1/4 is 12/64. And then finally, 1 minus 3/4 squared times 1/4 is 1 minus 9/16, which would give me 7/16 times 1/4 is 7/64. $31, $38, is that 50/64? $31, $41, $43, $50, yeah. 50 divided by 64. Well, it does reduce. We can at least get down to 25/32. And as decimal, 0.78125.
Jones,
Yeah.
hypothetical question. If we were doing this on a test and like instead of fractions, we were using decimals and we got an answer that was like 0.01 off, would that be okay?
Yeah, but you're not going to have a Riemann sum on the test.
Okay.
I don't plan on it. I have much better things in mind in store for your guys' fate. Great question, though. All right, let's take a look at it on the Desmos thing. If I scroll down, I can actually, it calculates it for us. And check this out. I can do it. I can set it where it does midpoint. Midpoint over calculates part of it, but under calculates on the left side. Over calculates on the right, under calculates on the left side for each rectangle. But they kind of balance out, like this little bit extra here kind of fills in the wedge here, and we get something like that. If we do right endpoint, we get something that's much lower. So let's go back to the left endpoint. If we raise n up, like let's make n 50, let's start with 25. It's a little tiny area. We still have errors along it, but 25 as opposed to 4, the error is a lot less. You guys see that? That's a shitload of error right there. But when we go to 25, it's a lot less. We go up to 50, it's even less. As we go to 100, you could barely distinguish that it's off. If I knew n equals 100 as the right endpoint or the left endpoint, and I do n equals 100 as the left endpoint, the left endpoint or right endpoint I get 0.66. The left endpoint I get 0.67. Is that the same decimal? Yep. 165 after that, 0.66 and 0.67. If I do the midpoint, I get 0.666665. What does this look like it's actually approaching? What's the real value look like? If I get n to infinity, what does it look like this would go to? Any ideas? What? Like an actual number. Like we've got n equals 100. If I can like up this to 10,000. What is that number as like a fraction?
Two-thirds.
Right? It looks like it's going to 2/3, right? So using Desmos, we saw as it goes to infinity. It looks like area goes to 2/3. So this rectangle method worked really well for quite a bit, but it doesn't work on every function. So they had to come up with other things. Isaac Newton and Gottfried Leibniz. So they're the ones that developed calculus at the same time in different parts of the world. And they found if f of x is a non-negative continuous function, like it doesn't dip below the x-axis. And we're looking at on the region A to B. If A of x is the area under the curve, is a function for the area under the curve, then A prime of x equals f of x. Yeah. That's the derivative of A, yeah. A prime of x. Or d dx of A of x. That makes it clear. Now we're gonna work one out with something that where you can actually find the area function. We're gonna make a straight line. And like find the area function and find the derivative and see how it relates. This is called the antiderivative method. once we see that it works, you start with f of x. And figure out what a of x has to be for the derivative of it, for the derivative to equal f of x. In fact, because two people did it at the same time, that's why we have two different ways of showing derivative. I want to say, I think the ddx, I think, was from Leibniz. And using the prime method, I think, was Newton. But I might have them backwards. There's a 50-50 shot I have them backwards. The prime methods using there's the height, the apostrophe takes a lot less time for now. When we get to a lot higher level, that prime loses its utility as soon as we start going into multiple dimensions. And then ddx really shines. So if you like the prime over the ddx, don't blow off the ddx. Get comfortable with it, because it's what really shows up later on. I'm off the screen and no one says shit. All right, so everybody looks like they're ready. Let's say f of x is 4x plus 5. And we're going from like -1 up until x. So this crosses at 2. And x is -1. I put in -1. I got 1 right here. So that's what we want to find. This is how we're going to do the area of this one. I'm sure there's a formula for trapezoids, because this is a trapezoid, but I don't know the formula for the trapezoid. I think it's 1/2 the sum of the bases times the height, but I'm not sure. I know I can do this. I can make this a rectangle and a triangle. So the rectangle has a height of 1 and a width of x minus -1. So a width of x plus 1. So the area of the rectangle will be x plus 1. So the triangle has the same width. W equals x plus 1. Because it's just as wide. And the height of it, that function is f of x. But we're shaving off that piece right there. So we're doing f of x minus 1. So I have 4x plus 5 minus 1 is 4x plus 4. And the area of the triangle is 1/2 base times height, which is 1/2. The base is x plus 1. The height is 4x plus 4. Yeah.
How'd you get the slope?
How did I get the slope? What do you mean? Where I didn't even use the slope?
4x plus 5. Is that not any?
It's just the function given to us.
I'm done. I didn't.
Good question. You missed that line. It sure as hell like, what the fuck is he doing?
How'd you get the width for the rectangle? I did miss that.
Width is b minus a. So if this is a and this is b, distance is always like x2 minus x1. In this case, b minus a. X minus -1. I'll be honest, that took me the longest time to fucking remember as a student. I could go flying through fucking calculus, but remembering where they got the fucking width from was not intuitive to me. But you go to a depth and I love it. So the area of the whole thing is x plus 1 for the rectangle plus 1/2 x plus 1 times 4x plus 4. What do we have here? We figure this out. This is 1/2 times 4x squared plus 4x plus another 4x plus 4. This is 4x squared plus 8x plus 4. I'll distribute the 1/2. And we'll gather everything together. A of x equals 2x squared plus 5x plus 3. Notice a prime of x is 4x plus 5. So we haven't done the antiderivative method yet. This was just showing how they're connected with an example. Now I'll let you finish writing it down, and then we're going to start thinking about how do we go backwards.
Where did you get the other x plus 1?
What do you mean the other? What does that mean?
Right there in red, there's x
This
plus
one?
1 plus, yeah.
It's the rectangle on the bottom. The width is x plus 1 and the height is 1.
Oh,
Does that make sense?
yes.
Okay. All right, so let's think about what we're doing here. What we got here. We've got a of x equals 2x squared plus 5x plus 3. And we've got a prime of x is 4x plus 5, which is our f of x. That was what was given to us. So could we have gotten past this really quickly to get a of x without doing this picture and this shitty formula, like figuring everything out? Because figuring out this formula only worked because I use shapes I know how to do the area for. If this was some crazy curve, I don't know how to do that. I know rectangles and triangles. So how do we go from here to here? Well, it looks like the 5 just added an x. And we added this an extra constant. It's a constant. We had 4, and we have x. It looks like the x went from the first power up to the second power. And in the process, we divided it by 2. That's knowing what a of x looks like ahead of time. That would get me 2x plus 5, or 2x squared plus 5x plus 3. Yeah, Preston.
So like, would you do like
It's exactly what we're going to do. It's a reverse power rule. We're going to do that in a second, though. That's actually where it's going. So, like, what is the power rule? What do we do on the power rule when we do derivatives? Now that this is 5.2, but Preston like identified it, so we're going to run with it. The power rule, what we do is step 1, we bring the exponent down. As a multiplier. In step 2, we lower the exponent by 1. That's what we do with the power rule, right? In words. Let's reverse this. And when I mean reverse, I mean reverse. Backwards order, backwards operation. Opposite operation. If I do that, reversing the order, instead of lowering the exponent by 1, I'm going to raise the exponent by 1. Let's say it was x to the n. That makes this look like x to the n plus 1 now. And then step 2, the opposite of bring the exponent down as a multiplier would be, instead of multiplying by it, dividing by it. So divide by the exponent. We multiplied by the exponent going one way, we're going to divide by the exponent now. We'll have 1 over n plus 1 times x to the n plus 1. So this would be the antiderivative of that. Let's see if we can apply that to the 4x plus 5. Let me let you finish writing this down. Everyone ready? Nope, now that's the writing. We're getting to that, Isaac. That's an excellent question. Isaac asked, what about the constant? How do we get this fucking 3 just popped up out of nowhere, didn't it? Let's look at that. We had f of x equals 4x plus 5. And that's kind of like x to the first plus 5x to the 0. So we're going to do this antiderivative of f of x. So x is going to go up to 2. We raise the exponent by 1. Divide by the exponent. That's going to happen on both of them. That goes up to a 1, and we divide by 1, which doesn't do anything. But we also have this weird constant, and we don't know what it is. We know we have that it's 3.
How do we know that we have a constant?
Because we found the area of the long form. We did it without the triangle.
We always have a constant.
Yes. This is I'll give it a name in a little bit. Let's just call it the constant for now. So my a of x is looking like 4x squared plus 5x plus c. How can we find c? Well, I'm going to bring that triangle back. We've been using x. What if I just said x equals 0? And then we're just looking at that's -1, that's 0. This is my y-axis, this is x. The area of the rectangle is 1 times 1. What is the area here? This had a height of 4x plus 4 times x plus 1. The 1/2 x, that's what we had. If x equals 0, though, this is that's excellent. All right, I'll just put it up real quick. Integration is anti-differentiation. That's the symbol we use. This is the expedited version. If you want a long one, go watch a longer video or show up to class. That'll work. C is called the constant of integration. Big F of x is the antiderivative. Dx tells us what variable we are integrating with respect to. This process is called integration. Integrating with a constant gives us x. And the easiest way to do it is just see, like, take a look at your derivative chart and go do this operation backwards. For example, we know the derivative of sine x is cosine x. So when we integrate both sides with respect to dx, it's kind of like this wipes out that. They cancel each other out. And we get sine of x plus some constant of integration. I think I can, oh, I can. Let me go grab useful handouts. I'll go over the basic properties in a second. The first page shows the derivatives. Second page shows the common integrals. They use U because there is a reminder. We'll look at what to do when we're doing like a chain rule in reverse and product rule in reverse later on. That gets more complicated, but the basic ones are these. I would say you should definitely memorize the first 6 trig functions. I don't know that this one right here is just doing a U sub. The 1 over ax plus b is just doing a U sub and making it 1 over u, ln of u, and we'll look at that in a second. This is doing some chain rule shit. Well, not in a second. Probably next week because Thursday's a test. You should know at least the top 3. The bottom 3 you can actually figure out by switching to sines and cosines. Some of these other ones are a pain in the ass to remember. You should be able to remember either the u. AU is one you should remember as well. It doesn't come up as much. Neither does the integral of ln of u. The inverse trig ones come up a lot. They really do. And when we get to like working those out, we'll look at them going in reverse. There's a bunch of miscellaneous ones. We will later on do U substitution. This is like the chain rule. And integration by parts is like the equivalent of the product rule in reverse. We're gonna be hitting those later over the rest of the semester. This was in the modules, it was the useful handouts. It's worth grabbing and like printing them out, flashcarding those bad boys. Let's go over some exercises. Let's evaluate the following. X to the 5th dx. Square root of t dt. And 1 over x cubed dx. Take a minute and try to figure out what those are. What do you guys get for this first one? You took the derivative. Do the derivative the other direction.
Oh. Five.
Plus, you do the x to the power 6 first, then do the 1 over. You can always, this is handy, you can always check your work. We bring the power down, lower the power, and the derivative of a constant is 0. And we get x to the 5th back. So you can always check to see if you got it right. Now, granted, so where it's just a single term like this and we're just doing a polynomial, it's quicker to check. Some checks are quicker than others, but you should be able to check every time. This is surprisingly unhelpful in the form it's in. This is a lot easier if we rewrite it as t to the 1/2. So, Preston, help me here. What is this?
It's just T.
No. It's got to go up a full 1. So 1/2 goes to 1 1/2, or 3/2. This is where dividing by 3/2 sucks. Multiply by the reciprocal. It was a good shot. I appreciate you trying. We also have that constant integration. Now, the way you can check, I go like Professor said, is it just t? Well, take the derivative of t and see if you get back what you started with. You get 1, which is not t to the 1/2. So you can tell doing a check. What about this last one? This is probably a little bit easier to rewrite as x to the -3. So remember, up a power, divide by a power. If I go up from -3, what do I get? -2. That one, the negative ones are easy to do backwards. If I divide by -2, I got 1 over -2. So that would just be -1/2 x to the -2. Yeah. You very much can. We could rewrite this as -1 over 2x squared plus c. In fact, it's probably the best approach. Put it back in the notation you found it in. So if it had negative exponents, leave it as negative exponents. If it didn't, put it back. Some basic properties of integration. Does anyone need this up longer? If you integrate a constant times f of x dx, maybe I'm going to use k because we use c as the constant of integration. This is the same as k times the integral of f of x dx. You can pull out the constant. Just like we could when we were doing the derivatives, you could pull the constant out of a limit. Similar idea. If you have the integral of f of x and g of x, two functions put together with respect to x, you can rewrite this as two integrals. F of x dx plus the integral of g of x with respect to x. And of course, the same operation works with minus. In fact, if you want to prove any of these, anything with integrals, to show the integral of, I'll use h here, equals capital H of x plus c, you have to show that d dx of h of capital H of x equals little h of x. So like proving the one on top, I want to show d dx. This would end up being k times big F of x plus c. It's actually k times big F of x plus c in parentheses, but since we don't know what c is, it's just a different constant when you multiply it through. Does that make sense to everybody? Well, technically we would multiply it through. This is like C1, this is like C2, but we don't know what it is, so we can just leave it as fucking C. And all is well. So to show the first one's true, we got to say d dx of k times f of x. Well, that's the derivative of k times, on derivatives, we can pull the k out. And that equals k times little f of x. So that showed how to do the first one. The other ones are similar.
Difference between the big F.
The big F is the antiderivative and little f is not.
Oh,
Big F is antiderivative of little f. This is universal. It's going to go with any letter. They even do it with the Greek letters, but how many of you know the Greek letter versus Greek capital letter? Man, we try to stick with the letters we know. That should say little. We're going to do some more stuff with this. Before we start 5.3 on Monday, you guys do have a test on Thursday. It is nowhere near as hard as the review. That review is godforsaken fucking miserable. I'm like halfway through it. I'm going to try to get the rest done today so I can upload the answer key by tomorrow. I assure you, I swear on my happy life, happy wife, the fucking review is much harder than the actual exam. With that, I will see you guys on Thursday. I'll be here at 7:30 if you want to come in early. I will be here at 7:30 this time, Matthew. Or anybody else that wants to be here early, get a jump start. Godspeed. But after the test on Thursday, try to like do some flashcards with these integrals. Makes it like try to memorize the integrations of like all the ones we took derivatives of, do the other way. So your polynomials, your trig functions, even the inverses, the inverses come up a lot in the opposite direction. They really do. So they're worth memorizing. And if flashcards don't do it for you, however else you do.